This stuff from chapter 12. There weren't many problems, but again, they probably were fairly challenging. I hope you persisted in them and aren't just waiting for the screencast, because otherwise it's going to be challenging for you come AP testing time. Formula for center of mass is the summation of the masses times the positions divided by the masses. So in the x direction, only these two masses, B and C. No, I was right. For C and D have a value of x other than 0. These two are at 0 on the x-axis. So 200 grams times 10 centimeters each. All that divided by the total mass, which is actually 700 grams. That equals 5.71 centimeters. Same with center of mass for y. These are the only two that have a y component that's not 0. Do the same thing, also 5.71 centimeters. Basically, this was asking now for part B if this object was rotated about this point, about point A. So if you think of it like a spear punching into the computer screen through there, and the other objects rotated around that, as if the lines connecting B, C, D, and A were very thin and massless, but rigid enough to maintain that square shape. So if we look at this, B is 8 centimeters away from A, so I would do mr squared for that because it's a point source, which acts like all the mass is at 8 centimeters away. For D, 200 grams or 0.2 kilograms is 10 centimeters away. For this one, 200 grams, if it was rotating about this point, I'd have to use Pythagorean theorem for that, and that's 12.8 centimeters away. So I convert the grams to kilograms, centimeters to meters, and I get these moments of inertia. So that's the total moment for the entire object if all three of these were rigid and rotating about point A. This has no moment of inertia associated with it because its distance is 0. For 24, the angular impulse is going to be the area of the torque versus time graph, just like regular impulse was the area of the force versus time graph that we saw earlier in the semester. So I did 1/2 2 times 2, that's 2 Newton meters seconds for this. If I want to figure out the change in angular velocity, then I could say the linear formula would be P equals m times v. This one would be L equals I times W, lowercase omega. And so really it would be delta L equals I times delta W. So something like that. And that's how I find out the change in angular velocity, and that's 0.5 radians per second. Another method would be to figure out the angular acceleration and multiply it by the total time. That's a little tougher because here the torque is not constant. I took an average value of torque since it looked like it was increasing linearly. It's 1 Newton meter divided by the 4 kilogram meters per second, which we were given as the inertia, and got 0.25 radians per second squared, multiplied that by 2 seconds. I think this is the more appropriate way to do that. I'm going to close my door for a moment because people are getting loud. 31 was a torque problem with a cat. Okay, so you've got 2 kilograms acting at the left end, 5 kilograms at the right end of the seesaw. Each side is 2 meters from the fulcrum. You've got a cat going off to the left side. We don't know what distance. Its mass is 4 kilograms. We're trying to figure out how far it would be to get things in equilibrium. So all these things, if you want to think about with torques as force times distances, you would multiply the masses times g. Those cancel out for the distances, so I don't really need to worry about that. And I end up getting that this distance is 1.5 meters. Now be careful, because that's not 1.5 meters along from the left end. It's 1.5 meters to the left of the fulcrum. For problem 32, got a 60 centimeter diameter tire. Immediately just change that to radius. Speed of the car is 20 meters per second. So if I want to get the angular velocity, I look at 20 meters per second divided by the radius is equal to the angular velocity. So v divided by r is equal to angular v, or wonky w. So that's 66.7 radians per second, but it asks for it in RPM, so that's easy to convert. Radians per second. There's 60 seconds in a minute, and there's 2 pi radians in 1 revolution. So I just make sure that my units cancel out. Notice I show all these steps as you should with any conversion, or if you're doing corrections. So the speed at the top is going to be twice the average. The speed at the bottom is 0. That was mentioned at the end of the chapter. All right, so in this case, we've got an object. It's a rod, 2 meters long, 500 grams, 120 RPM. So that is 2 RPS, 2 revolutions per second. So the moment of inertia of a thin rod rotated about its center is 1/12 ml squared. So to look at that, I've got 1/12 mass, total length squared. That's my moment of inertia. If I want to figure out the angular momentum of this thing, that's a glob there, I don't know what that is. I need to figure out the rate of rotation in standard units, which would be radians per second, and multiply it by the moment of inertia, and that's it. So it's 2.09 kilogram meters squared radians per second. A little odd. I guess you could say kilogram meters squared per second. 62 is kind of a fun problem. It deals with whether or not someone eating their lunch there, and they're like sitting with their knee up and stuff like that, looked a very bit relaxed on a on a beam here, is safe for if this cable is rated at 15,000 newtons. So the key thing with this is putting this as your fulcrum, I think, because the wall could have unknown forces acting on this horizontal beam, and therefore we want to eliminate that as any possible source of torque. So if we pick that as a fulcrum, all those forces from the wall are at 0 meters. They cause 0 torque. So in this case, I'm looking at clockwise torque equals counterclockwise torque. The beam is 1,450 kilograms. So I'm going to assume that that is acting at this particular spot, which is 3 meters, which is halfway out. So mg times that distance, plus the person who's 80 kilograms is at 4 meters away from the left end, so that's mg times that distance. So I get a total of 45,766 newton meters of torque clockwise. The cable has to exert an equal amount of torque counterclockwise, but it's not pulling vertically. It's pulling up to the left. So only the vertical component of that, acting at that 6 meter location, would provide the amount of torque equal to this. So thinking about that, this F cable times sine 30 becomes 0.5. That's 6 meters. Again, I was sloppy about labeling that. So I ended up getting that the force in the cable is 15,260 newtons. That is greater than the rated strength of the cable. So that person sitting there should feel unsafe and certainly should not go out further. Goes in a little bit, wouldn't be so bad. So these are the key ideas in terms of what we're doing. For 69, this is very similar to the example that I posted online. I think I did it as an example in both my classes, but a couple people said they don't remember that. So either they were out or I did not do that in one of my classes. But I urge you to go back and look at the examples on my website. So the key thing I think of is you can think of this as a torque problem. You can think of it as a force problem. So I tend to do this as terms of method 1. So it says that the friction is causing 0.5 newton meters of torque. This is a 6 centimeter radius because it says 12 centimeters in diameter. The mass of the pulley is 2 kilograms. And friction on the axle causes that amount of torque. So finding the time for the block to hit the floor 1 meter down, if we find the acceleration, we can figure that out using a simple like y equals 1/2 at squared. So in this case, I'm going to use F net over M equivalent. So the torque, or basically the force causing this thing, minus the force causing this thing, minus the force caused by friction will give me my net force. So to find the force of friction, I'm going to use force of friction times distance is going to equal the torque. We know the torque caused by friction, 0.5 Newton meters. And we know that we could think of that as acting at 6 centimeters from the center. It may or may not be, but we could think of that to help us figure out the equivalent force of friction, which was 8.33 newtons. So when I get that, I get 39.2 minus 19.6 minus 8.33. The mass I'm giving is an equivalent mass. This mass is 4 kilograms. This mass is 2 kilograms. The mass of the pulley, equivalently, if it's a solid disc, is not 2 kilograms, it's 1/2 of that, which is 1 kilogram. So overall, that's how we would use that doing forces. Torques I could figure out down here. And I could keep the friction as a torque. I could convert these gravitational forces to torques. And I could think about the angular acceleration that way. I could go back and convert that to linear acceleration using A equals alpha times R. Get the same thing. The last problem here is an example of the parallel axis theorem. So we have a disk rotated not on the center but on the edge. It's a solid disk. So there's a torque that's caused by the fact that the center of mass is 30 centimeters away from the edge, and it's causing it to fall down. So that gravitational torque when this thing is initially off to the side would be maximized. That's mgd, 14.7 newton meters of torque. We need to figure out the moment of inertia. Well, that's 0.5 mr squared for a solid disk. But the parallel axis theorem says if we are rotating about this edge, that's the mass times the distance from the center of mass squared, which in this case happens to be 0.3 meters as well. So we get that the total moment of inertia is 0.675 kilogram meters squared. The torque we figured out before. Get the angular acceleration. Then I can use energy to think about this for part B, where it's asking about the rate of rotation at the bottom. EI equals EF. We've got gravitational potential energy and rotational kinetic energy. Be careful, I would not call that as being linear kinetic energy as well at the bottom. We can talk about that in class, but unlike the rolling race where things are going down the ramp, this thing is not moving from the location. It is not rolling down a ramp. It is rotating about a fixed point. So that is only rotational kinetic energy. Hope that helps. That's how you use the conservation of energy to get the angular velocity down here. So hope that helps. I know these problems are not easy.